Everyone. So we are returning from our lunch break. So we are going to continue with Dr. Dimagi presentation from Agricultural Research Agency, Embrapa. So Dimagi, feel free to share with us your research. Afterwards will be Professor Murilo from UNICAMP, and I will apologize. I'll have to leave for a committee, but afterwards I return. But have a good afternoon, everyone. And Dimagi, thank you.
Thank you, Jamil. Thank you very much for being here today, and thank you, Edson, for inviting me. It's a pleasure to be here. I'm a former PhD student also here. I've been longing for like 6 years collaborating in the department, so it's a pleasure to collaborate even more. And now we're presenting Embrapa, so really happy to be here, and thank you very much, Bridget, for also being here today. So I'm going to be presenting some of these slides are just like some institutional slides, so Bridget can have some more knowledge about the corporation. And then in the end, I'm going to present some of the work that I've been working for the last couple of months, because it's couple of recent work, even though some of them I've been working for the last years as well. So to begin about it, Embrapa is a Brazilian agriculture research corporation. The main focus of Embrapa is to develop agriculture in the tropics. So it is the main research agents focused on agriculture in the tropical area. Is it working? Yeah. So it was created in 1973, so it's about 51 years old. The main focus is to develop technologies for a genuine tropical agriculture and livestock model. It has more than 7,000 employees. Most of them, it is researchers with more than 2,000 researchers. Very qualified, as you see there, with more than 90% of them are doctors. Then we have some more analysts, about 2,000 as well, some more 2,000 assistants, and 1,200 technicians. As you see here in Embrapa, it's spread over the entire country. So we have campus, we have 43 decentralized units. Those are research centers. And as you see here in the map, they are pretty spread from the north point until the south point, covering all of those states. And the difference between those research areas, it is divided into 3 points. You see here in the pink dots, the pink dots are ecoregion research units. So for example, we have Embrapa in the Western Amazon, Embrapa in the state. So the focus of those units is to develop the state or a biome. We have then in the green, in the blue dots, research product. So imagine, for example, Embrapa rice and beans here in Minas Gerais. We have in the south Embrapa grapes and wine. We have Embrapa wheat. So the focus of those units is to develop a single product. But we also have units that are focused on basic themes. For example, as we have close to here, Embrapa instrumentation here in São Paulo, just around 2 blocks far from here. I'm going to be talking about more that in detail. But we also have some other examples. For example, Embrapa agroenergy. We have Embrapa Environment, that is also close to here. Embrapa Digital Agriculture. So we have those 3 types of research centers. In partnership, we have around 28 contracts and agreements, 30 partners, and those are spread over the world, most of them in Germany, United States, Israel, which also is focused on agriculture in different contexts. So we have those partners that are partners just not only for just products, but also to share new technology in the development of new technologies. So summarize some of the work that I've been doing in 2 of them. The first one is Embrapa Agricultural Instrumentation. That is the building that is just 2 blocks far from here. I don't know if you had the opportunity to see that. Perhaps in the way that you're going to be walking or passing by, they can show you. This is how it looks like. And the focus of this research center is produce technologies, innovations, sensors, methodologies, or even materials that's going to be contributing and increasing the productivity and sustainability in agribusiness. Some of the examples that these research centers had developed, here we have some example. The first one, it is a sensor for soil water stress management and agriculture control. The second one, it is a multi-parameter probe for aquaculture that's going to be able to measure parameters in real time or even remotely, as you see there in the picture. A third example, it is social technology that's applied for rural areas. So that it is a very simple but super applied. There is a septic tank for a digester. So in rural areas, they're not going to be collecting the wastewater. So they're going to be just storing the wastewater in those tanks. And so that's going to be enable the anaerobic digestion of wastewater. And one example that I've been working with for the last 4 years, it is in development of a low-cost soil moisture sensor for irrigation control. I started developing that during my PhD. And so that probe, it's enable the monitoring of temperature, soil conductivity, but also soil moisture in 3 different spots, up to 1 meter depth. It works very well. Here in this example, you can see that it can be installed in different areas in agricultural zone. And so it's going to be connecting those data to a monitoring station, and then you can have real-time monitoring of soil moisture, and then it can be coupled with agriculture irrigation system. So you're going to be reducing first the amount of water that is going to be used on that system, but also it's going to be reducing the amount of energy that is used on agriculture. So it's going to be developing the sustainability in agriculture, but also it's going to be reducing the amount of water that is used and the amount of money that is used on agriculture. So that is actually very coupled with you were talking about before, that how much water are going to be using in agriculture. So that is one way that Embrapa is contributing to reducing the amount of water that it's taking out of aquifer, but also in surface water. And now moving on to Embrapa Environment, which is the one that I'm working at the moment. The goal for that unit is the research and development, innovation that is focused on the interface between agriculture and the environment. It's located close to Campinas, so it's pretty much in between São Carlos and São Paulo. It's around 45 minutes out of Campinas, so it means 2.5 hours far from here, so it's not that far. So the focus of that unit, it is pretty much those 4 that I kind of summarize here. The first one, it is climate change and agriculture. The second one is biotechnology. The third one, impact assessment of agriculture. And the fourth one, sustainability production system. And just to summarize one example that they are been developing, it is when they were able to couple those 2 examples of focus of the unit, which is climate change and agriculture and biotechnology. And so the project that they are actually running, it is the bioprospecting of microorganisms that is used in the Caatinga. Caatinga is the same area in the northeast of Brazil. And so they were running some field tests there and collecting some of the microorganisms that are living on that very dry area. As you see here, the mandacaru, which is a type of cactus, a species of cactus there. So they were able to isolate some of the microorganisms that are living in partnership with that species, and now they're using that microorganism into corn and soybean, and so turning those species of agriculture more resilient and resistant to dry period. So now increasing sustainability and even prevent damage of climate change and drought scenarios into agriculture. Another project I'm actually running and working with, it's related to pesticides. And when we were talking about agriculture and especially water management, most of the time we're just talking about quantity, and very rarely we're talking about quality of that reservoir or the water that we are going to be monitoring. And so, unfortunately, Brazil is well known for the use of pesticides in control of some insects, bugs, or some other plants that are living in agriculture. So we are unfortunately increasing the amount of pesticides, and we know very little about how those pesticides are going to be lasting for, or even if they are going to be out of the agriculture zone. So the project that we're going to be running, we're going to be having a field monitoring that is quite innovative and challenging, where we have a network of 63 watersheds in Brazil, and they're going to be spread, and at least one state is going to have at least one single point. Some of these states are going to have some more of those watersheds that are going to be monitored. We're going to be monitoring more than 20 pesticides, and then the focus then it is later to identify the hydrological shortcuts and the hydrological signatures that's going to be connected and linked between the pesticides and the environment, for then later to see how far the pesticides can go, and if that's going to be contaminated, not only if it is contaminated the surface, but also in the future if it is somehow threatening the aquifer. And so we're going to be talking not only about quantity, but then we're going to be adding a new variable that is even considerably more important, which is the quality of the water that it's somehow recharging the aquifer. And I think, if I'm sure, the network that we are running already, it's conducted by SGS. So somehow like we are connected. And thank you very much for that. So that's the project I'm going to be working with. It is still in the beginning, but the monitoring is already running. And we have the first field data, and we're analyzing, so that's the ongoing project. So here's my contact. We can be sharing more and can be talking about more about agriculture and this project. Thank you very much today.
Thank you so much for your presentation, Dimagi. Now I think we can invite Professor Murilo to present his work on University of Campinas. And after his presentation, then we can have the questions and answers for everybody, and we can do, I don't know. Yeah.
Hi everyone, my name is Murilo. I'm glad to be here. Thank you, the Professor Edson and Jamil and all the LHC group for the invitation. In this presentation, I will briefly present to you our recent young research group. Here with me is my students, Mateus and Priscila, and they will follow me in this presentation. So, our group is the Hydroinformatics Lab. We are at UNICAMP in the Limeira municipality. And This is a picture of us. As I said, we are a small group. So here we have me, the other professor, Dagoberto, Priscila is here, Mateus is not in the picture, Maria Fernanda, Mateus, Maria Fernanda and Mateus, they are undergraduate student, Guilherme is also undergraduate student, and Tatiane is a PhD student, and Leticia is an undergraduate student. So since we get some funding this year, we started this research group, specifically in January 2024, and we are consolidating ourselves as a research group in Brazil. So we focus on using technologies to solve urgent societal problems. We follow the hydroinformatics concept vision of Michael Abbott and Professor Daniel Locks. They said that hydroinformatics is a technology that combines information and communication technologies, and also optimization and simulation techniques, altogether with big data, data science analysis. So we are not working in the field yet, not still yet, but we are using the big data, the available data, to make some discoveries. Our mission is to advance the understanding of how human activities and climate variability impact environments. As Professor Scanlon said, we are trying to evaluate what is climate variability impact and what is human activities impacts in our research. Impact environments that depend on surface and groundwater resources. To achieve that, we use advanced tools in information and communication systems. As I said, data science, computational modeling, to better understand, simulate, and manage water-related challenges. So we are starting as an informatics lab in water resources issues. Our scientific research focuses on surface and groundwater process. However, we are now focused on surface water problems. And I'm to enhance understanding or develop solutions and technologies to create sustainable and resilient societies. So, some issues that we have addressed: stormwater drainage, flood warning systems, droughts, groundwater, hydrology, and a little bit of hydraulics of rivers and lakes. Here is my undergraduate students, Laura and Graziella. They are actually studying the Tubarão aquifer system. I can say the shark aquifer system in English. Yes, very strange name. Specifically in the municipality of Limeira. So they are performing some simulations using ModFlow and the groundwater pumping data available for several agencies. This is a project in and our partner are BRK, and our goal is to understand the impact of the pumping and future the pumping on the water level in the aquifer. Understanding the impact of climate variability in the Tubarão aquifer system and its effects on groundwater availability and pumping. It's a initial study. We have started this year, but it's a beginning. And we would like to highlight the importance of hydrogeological monitoring network for continuous updating for simulations to be our key company. Now, Priscilla, please come here. The floor is yours.
Hi everyone, good afternoon. Hi professors and students. Thanks for the opportunity of being here today. My name is Priscilla. I'm part of the Hydroinformatics Lab research group. I'm from Minas Gerais and I'm environmental and sanitary engineer and master in sanitation, environmental and water resources at UFMG. And now I'm PhD student in technology at UNICAMP with the Professor Murilo, my advisor. My doctoral research project is illuminating flash draw in Brazil. I'm at the beginning, but I will talk a little with you about this. Here we have some causes to draw, specifically anthropogenic causes to draw. For example, increasing water consumption caused by excessive irrigation, population growth, land use and land cover change caused by, for example, overfarming, urbanization, deforestation, and soil degradation, and the greenhouse gas emissions that cause anthropogenic climate change. So, the flash draw. Flash draws have been occurring more frequently worldwide with fast onset and development that challenge forecasts and adaptive actions against draw for society. And in Brazil, however, there is not a broad agreement about the flash draw across Brazilian territory. Events for Brazil had been predicted in a global generic assessment and may have been underestimated. So, to help identify and conceptualizing flash draw, the following principles were postulated by the literature. So, the principles are rapid onset. Flash draw should be within a few days to weeks, distinguish them from the gradual development of conventional draws. The severity of the draw is expected to increase rapidly, allowing a transition from moderate to severity draw in a short space of time. And the severity. The outcome of the event must be important enough to classify it as a flash draw. So, how to identify? There is no major consensus in literature, but the intensification of a variable, such as evapotranspiration, for example, followed by the decline of soil moisture, is normally used in the literature. So, how identify? It's color, red color, okay? Decline is soil moisture from above the 48th percentile to below 20th percentile, and simultaneously there must be a reduction in evapotranspiration to 350 or less. And the duration. The duration is the period that begins when soil moisture falls below 20th percentile and ends when it rises above 20th percentile. But why? Are these criteria also valid for Brazil too? And here we can observe the difference in behavior between flash draw and slow or conventional draw. So Here you have the scientific gaps. The first, once flash draws are occurring in Brazil, do they have the potential to become the new normal in futures of draw? How to validate the occurrence of flash draw in Brazil? Which phenomenon can be measured or observed to confirm the existence of flash draw? Maybe we will pinpoint which new quantitative metric can improve in Brazil, or what quantitative metric can be used to define flash draw from soil moisture, for example? Which hydrological variables can be used to detect flash draw in different regions or biomes of Brazil? And what anthropogenic actions may trigger and accelerate the occurrence of flash draw? Which draw index can be used to detect flash draw set, development, and severity in Brazilian biomes? And finally, how will climate change the impact on flash draw? So, the purpose is to assess changes in onset speed of draws, their severity and duration in Brazilian territory, and to achieve this target, quantitative and qualitative by remote sensing datasets will be used, such as evapotranspiration, soil moisture, and land use and land cover changes. Well, Brazil is a country of continental dimensions, different landscapes and high elevations. So each biome has a specific climatological and ecological features, with different populations and occupations patterns influencing the frequency and intensity of draw impacts. So, our study area is the Brazilian territory, covered by nearly 8.5 square kilometers, classified according to its 6 biomes: Amazon, Cerrado, Atlantic Forest, Caatinga, Pampa, and Pantanal. And here, that's my working plan. There are some planned activities of my doctoral research project. I'm at the beginning. I'm on the 3rd trimester or 2nd semester. And some activities are complete and others are in progress, and many activities are planned. I will just highlight something for you. For example, the milestones: submission of a review article to a journal, participation in a teaching internship program, PhD monitoring by UNICAMP, my qualification exam, writing a scientific article with the preliminary results, participation in international event, ADU, the next year, submission of 2nd article to a journal, preparation of 3rd scientific article with the results of the project, send the final version of the thesis to my advisor, and finally, defense of the thesis to the examining board. And that's it. Thank you.
Hi, good afternoon, everyone. My name is Matheus Domingos. I studied sanitary and environmental engineering at UFMT, and just 3 weeks ago, I started working with the project with Murilo at UNICAMP. And thank you very much for the opportunity to present my research today. The title of my project is Urban Flood Prediction, where I explore the use of machine learning algorithms, rain gauge data, and satellite imagery. So I'm going to talk a little bit about the problem and the solution behind it. Traditional hydrological model for flood prediction is rely heavily on physical process. However, they require extensive and high-quality data sets, often spanning long historical periods, to accurately simulate the physical process governing flood events. So, given the limitations of traditional modeling, machine learning and artificial neural networks like long short-term memory, ensemble learning method, and convolutional neural network offer a promising alternative. So the main goal of my research is to verify how well machine learning models works in flood prediction with scarce data. And I'm focusing on the Limeira region. So in this research, LSTM networks and the ensemble method will be employed to leverage the temporal data available from the SEMADEM station. And together, additionally, satellite imagery from Sentinel-1 or GPM, along with supplementary data on terrain, that includes digital elevation models, soil type, the hydrological soil group, and imperviousness will be integrated using CNNs like UNET. So I have different methodologies. One that means to use the temporal data from SEMADEM and test the accuracy of LSTM networks and the ensemble method. And the other one is to use convolutional neural networks like UNET with satellite imagery and any supplementary data needed. So I'm going to talk a little bit of the scientific gaps that my research aims to fill. The first one is about the ensemble model, if it will demonstrate greater accuracy in flood prediction in the Limeira region compared to the LSTM model, due to its ability to combine predictions from multiple individual models, which will reduce uncertainty and improves the robustness of the predictions. The other one is if the UNET model will perform better in flood prediction compared to other models, due to its ability to capture and process complex spatial information from satellite images. Then, in the UNET model, which combination of data will better perform the UNET model? The rainfall, the imperviousness, the hydrologic soil group, the digital elevation model, which combination of this data will perform better in the UNET model? And which of the three models will have the best overall performance in flood prediction? And finally, I'm going to discover if machine learning is a good alternative for flood prediction in a scarce data region. So this is my study area. The red dot is the SEMADEM station, where I'll be gathering the rainfall and the water level data. And that's the basin based on the SEMADEM station. In yellow, we have Limeira. So, talking a little bit about the methodology, the ensemble method. First, I will collect water level and rainfall data from SEMADEM. Then I'll be pre-processing the data with Python algorithm. And then with the prepared data, it will be subdivided in training sets, validation sets, and testing sets. Then I'll build models and test those for selecting the model with best accuracy. For the LSTM models, there will be no building. I'll directly use the LSTM. Then for the CNN, the UNET model, there will be that data identification and collection, like flood event reports, satellite imagery, and flood influencing data. The flood influencing data includes spatial data and multiple rainfall gauges. Satellite imagery will be from Sentinel-1 or GPM. The spatial data includes the digital elevation model, hydrologic soil group, imperviousness, and rainfall data from multiple rainfall gauges. Then they'll go under pre-processing to create the first one, raster maps, and the second one, flood inventory maps. And those two will compose the UNET model developing, while the flood event report will be used as ground truth checking to flood extent prediction. So I'll be using the maps that will be created in the UNET model, and I'll compare with the flood event report to see if it works. So this image here translates how UNET can identify the complex characteristics of an image. And that concludes it. Thank you.
Thank you so much, Professor Murilo, Mateus, and Priscilla, for your presentations. I wish all the success for you guys for the Hydroinformatics Lab. You are working with very hot topics today, and particularly flash droughts. I think it's a very important topic here in Brazil that remains largely unexplored. I think it's better for us to keep with the presentations and then do a final question and answer with the broad audience. Yeah. So now I invite the group of Professor Didier, the research group. I don't know your names, but if you... Yeah, then we will have a break, a coffee break, and then we will have another student from Professor Didier after the coffee break. Because we need some time to... Yeah, to fix that. Yeah.
Okay. Hi everyone, my name is Vinicius. It's a pleasure to be here. Today I will talking about a tree project for the Telahia group. We are using the stable weather isotopes to study convective rainfall system in the Amazon. So my presentation will cover introduction, methods, results, and conclusions. As you know, precipitation is crucial for groundwater research. So in our group, a big change is to understand how the climate impact, how climate change impacted the precipitation in different temporal and spatial scales. So let's go. And here we have an amazing picture, and it illustrates the Amazon River Basin. The Amazon River Basin is an extraordinary social ecological system connected by water flows from the tropical Andes, mountains, Amazon lowlands, and Atlantic Ocean. Important hydroclimatic component is the convection. Convection moves the energy from surface to the atmosphere, generates rainfall. Recently studies suggesting that convection in the Amazon is increasing. So it's a problem because strong convection generates an extreme rainfall events, and this impacted the population, especially living in risky areas. Another crucial component is the forest evapotranspiration. The evapotranspiration generates humidity, used locally and transported to the South America, providing a main continental source of moisture for precipitation. Here we showed two amazing papers. They show the role of the forest evaporecirculation and the intertropical convergence modulation, especially during summer rainfall. These papers emphasize the use of stable weather isotopes, has been and continue showed how stable weather isotope is crucial to understand water flux in the Amazon. In this context, Didier groups have been carried out 3 projects, 2 postdoctoral projects in the Amazon and a master project. So it is a researcher participating in this project. We have UNESP team, INPA team, and the international partners from Costa Rica, the USA, and university in Europe. So in this manner, DJ talking about stable theory. So I can simplify this topic. So here, the theory excess is another isotopic component. The theory excess is used to understand the evaporation and moisture source and transport. So we combine the theory excess and oxygen. We can understand this process in rainfall. So rainfall influenced by evaporation. We have higher oxygen values and lower the excess values, while rainfall inflation by successive condensation, we have lower oxygen values and higher the excess values. So, in this picture, we combine the sample time scale and spatial and temporal scales of atmospheric system. So, what are you looking for? Depending on sample scale, a unique insight provides different interpretations in isotopic signature. For example, a mountain collection represents a sum of events and in a unique isotopic signature. So provide a large climatic variation and large atmospheric system. For daily collection, we have a few events, and we provide understand about moisture transport, large scale circulation, and convective activity. In high frequency or inter-event, it's a minute collection. We can understand the local process, especially the cloud process, like formation, evolution, and subcloud process during fall raindrop. In our project, we have 2 sample sites. The first is in Manaus City. It's a daily collection. So since last year, we have collected daily samples. The second site is the Aro. Is localized in the Amazon rainforest. Last year and this year, we have made 2 intervention campaigns. The results of stable weather isotopic composition were analyzed in partners labs in Poland and the USA by laser absorption spectrometry. Here, the Aro is a Brazilian and German collaboration. The main goal of the ATO is to understand the Amazon rainforest and its interactions with the soil and atmosphere below. In these pictures, we can see the long journey from Manaus to the ATO. Here we have a long a transport by road, dirty road, and também by boat. The ATO project the ATO project have 2 smaller towers and one of 325 meters tall, as illustrated in these pictures. These towers measure a complete CO2 and water flux system, and as well various meteorological parameters at multiple levels. Further, we use micro rain radar to provide a vertical profile of rainfall and classify it in rainfall types. Automatic weather station, GOES satellite images, high-speed back trajectories to identify the moisture transport, R5 reanalysis for synoptic evaluation, and WAN 2 layers to track local humidity in our sampling points. So, about manual results, we have here a picture of the last year's precipitation and temperature compared to long term. We observe here a high rainfall amount between December and May, and reduced in precipitation amount between May and November. Follow this pattern, we observe here the isotope composition. So between February and April, we have lower oxygen aid values, and from May to July, we observe isotopic enrichment. Here we have a classical scatter of the oxygen and deuterium, and the regressions and equations line. With this scatter, we try to analyze a climatic aspect of the isotope composition in a unique point. So these values and this isotopic distribution indication a regional process. So what process is this? We can explain here. So we have back trajectories for a high split. So we have a clear pattern. So north back trajectories and south back trajectories. So in this period, when we have north back trajectory, it's the period of ETCZ intertropical convergence zone modulation. So during this pathway, we have successive condensation process, depletion, the humidity and rainfall in heavy isotopes generated these lower oxygen values. So for salty back trajectory, this successive condensation occurring in lower humidity, and which results in isotopic enrichment. Here we have the intervents. We have here a box plot for all intervents collected in Manaus. So we can put isotope composition and meteorological. We observe here a decrease in isotopic valence in second events during the same day. These lower oxygen and deuterium and deuterium excess values occurred together lower brightness temperature. This parameter we extracted from the GOES satellite images. So lower brightness temperature indicated a strong convection, So we have here lower oxygen deuterium in DXS values in a strong convection formation of a rainfall. The convection alone, only convection doesn't explain. It is isotopic distribution. So we analyze other meteorological parameters, such as total column water, narrative water vapor flux, and track evaporation. So these lower DXS values in here could be explained by input of local humidity, as shown in these maps. We can see in spatial maps and in temporal variation. Here we have all intervents collected. So oxygen, DXS, temperature, relative humidity, rainfall rate, and Gauss-Brightness temperature. Specific in this part, we observe a decrease in DXS, showing in detail this local humidity input. So we can see in a temporal way this local humidity influence the isotope composition during the event. Here, arrow intervents and a box plot of isotopic in all meteorological data set. We observe here a clear decrease each day, then increase with positive values. So this isotopic pattern could be explained by predominant vapor flux from the Atlantic Ocean. So in blue here, these negative values indicate a flux from the Atlantic Ocean. So a successive condensation process, depletion in heavy isotopes, the vapor and consequent rainfall results in this isotopic pattern. So we observe a change here in isotopic pattern. You can see in a direct way a change in vapor flux here and here. So we see a change in isotopic composition combined to a change in vapor flux, indicating how the stable isotopes respond to a meteorological influence. Here we observe the intervents. So we detail longer events with a large isotopic range. Here we have a Gauss image, and we observe evolution of convective systems. Here we have a vertical profile of a micro rain radar, and the isotopic composition. We observe variations in isotopic composition in here, and this variation reflects a change in the mechanism of raindrop formation. So this mechanism, as illustrated by irregular blank bands in here and here, that indicate lateral dispersion of hydrometeors. This is a typical convective process in convective cloud. So in conclusions, we see the isotopic composition of rainfall reflects local and regional process in the Amazon. For regional aspect, moisture transport is the best process, and we can see with the daily sampling and the average median values of intervents. About the local aspect, cloud microphysical and local vapor or local humidity input, we can see by intervent evaluation. So in this presentation, we showed how the stable water isotope is essential tool and tracer for understanding hydroclimatic process in the Amazon. For the second campaigns, we are waiting the auto data set. So we combine in interventions analysis, vapor isotope composition and rainfall. So this is a first approach in the Amazon. And with vapor, we can try to improve our interpretations about the convective systems in the Amazon. So that's it. Thank you for your attention.
Thank you so much, Vinicius, for your very nice presentation. Thank you so much. Now I invite Bruno to talk a little bit about his experience in research. Bruno is also a master student of Professor Didier. And after Bruno, I think we can have a coffee break and then return with more presentations and then to discuss about the...
Good afternoon, my name is Bruno. I am master degree student at the São Paulo State University and also in postgraduate program in Geosciences and Environmental in Rio Claro City. My research grant is by São Paulo Research Foundation, the FAPESP, and the name of my project is Impacts of Seasonal Variation in Groundwater Availability on the Hydrological Regime of the Pantanal Basin. So, in this case, Pantanal is my study area. Pantanal is a sedimentary basin here in Brazil, and a wetland too, a very important wetland to Brazil, and to the world too, I think, is important because so many reasons like species and traditional communities depends of these hydrological dynamics in Pantanal, and is one of the largest wetland in the world, and also is important because it's the only active sedimentary basin here in Brazil with active sedimentation process. This sedimentation process is very important to the Pantanal because the landscape change process is very fast because of this. The riversway change is a very fast process because this sedimentation process, and we have another controls too, like the climate. So the rainfall rates is more outside of the basin and very lower in the Pantanal area. This is a good point because the water is very important for the Pantanal. It's a wetland, of course, but so much of this water, this rainwater, coming outside of the basin, and we have just a little of rain in the area. Also another controls like the relief and the geology, so the terrain is very higher in the edges of the area, the north edge and the here, and very, very flat in the Pantanal area. About the geology, we have basically just sandstones. This is a good point too because here we have just unconfined aquifers too, and the Paraguay River is the main river here. He starts in the north, they go away to the south, and we have these another rivers, the Taquari River and Rio Negro River. The flow of, in this case, starts in the east and go away to the west to find the Paraguay River. And the objective of my work in this case is understand the impact of this groundwater to the water cycle, in keep the surface water or not keep the surface water. So how works this groundwater in the dry season to keep or not the surface water, the water levels, and how works the
the rain dynamics in this hydrological dynamics in Pantanal too, because how I said, the rain water coming with the rivers so much of outside of the basin, and this is a good point for this dynamics. And we use Gracie data and by NASA, the groundwater, the total water storage, and also water levels from National Agency of Water, the ANA. And this is in situ data, and also this hydrological model for the rain rates, the GPM. About my work plan, we divide. Pantanal have a very complex hydrological dynamics, so we have here lakes area is like 7,000 of lakes here. Here flooded areas, seasonal flooded and not seasonal flooded areas, and areas with not flooded dynamics. So it's very complex, and in work plan we divide with the fluvial fans in Pantanal. We have 9 fluvial fans, and I start with the Taquari mega fans, the largest fluvial fans here. And how I say, the terrain is very higher in this edge and very flat in the area of the Taquari. The rocks here are mainly sandstones, and finally here we have the groundwater storage anomalies for the last hydrological year. So we can see in this case, in the negative, in the red colors, the negative anomalies, and in the blue colors, the positive anomalies. And in this case, we can see the dry season and the rain season too, and how this works in the Pantanal. Sorry, in the Taquari megafan. We select some points in Taquari to see the difference in the groundwater storage anomalies. So the point A in the starts of the Taquari River, the main river in this area, and a point B in the middle of this river, and a point C in the final where the Taquari finds the Paraguay River, and also a point D here in the north area, and a point A, where we can find so many lakes. So here we have, how I said, 7,000 lakes. And here we have the average for the 20 years time for the here the dry season and here the rain season, and we can see a difference in the point A in this area and the another points. So about this and the rain rates, we can see this is a correlation between the groundwater storage anomalies for the Taquari megafan and the rain rates. So we have some correlation, but it's not a good correlation. But when we see the correlation just for the point A is the same, the point B too, and in the point C too. But when we have a correlation between the groundwater storage anomalies of the point C and the rain rates of the point A, the correlation is a little better in the second case. So how I said, the rainwater coming so much outside of the basin, and the flows is the east for the west. So and here we have just a little of the rain. And finally here we have the groundwater storage anomalies for 2 years in Taquari, mega fun. And in this case, in Ao Pantanal and also in Taquari, we can see a drop in all of the hydrological time series. And here we have the 2007 years, a normal year, and in the same scale of the color, the year of 2021, and it's very different. I select a month of this normal year, the August month, and here we have in the right side this month the total water storage, and for the same time here just the groundwater storage. So here we have the groundwater storage, the surface water, the soil mixture, the total water storage, and here just the groundwater storage, and in the same scale of the color. So we can see maybe some effluence area in this case, and this area is the area of the fluid dynamics. So here we have fluid, seasonal and not seasonal fluid areas, and this is maybe an important dynamics for the Taquari mega fun. And this is a little of my objective, understand the relation between the groundwater and the surface water. I will interrupting my research in the ends of this month to take a time abroad in the Washington State University, and this time is 6 months, and I will in September. And we will work with hydrological time series. So here we have the groundwater storages anomaly for a station, the São João station, and the water levels for this station, and a good correlation. But in this second case, we have a groundwater storage anomalies too, and the water levels of the river here in this station, and the correlation is not so good. But for this station, if we use 2 month delay, a step of 2 months in the water levels rivers, the correlation is so much better. So we have this dynamics. How I say, the Pantanal is have very complex hydrological dynamics. So we have so many cases, and in the United States, here we have a normal year, the 2005 year, and here the groundwater storage, and the line is the rain rates. And for the same station here in the right, we have the 2020 year, and it's very different. So we have a drop in all of the hydrological time series in Pantanal. And the objective in this time in the United States is use a machine learning model to learn the relation between these two hydrological time series, the groundwater storage anomalies and the water levels, and to predict some gaps. So here we have a sample, and in red color we have the gaps predicted, and in the red colors your data. And also with this, maybe predict some trends and data for the next of the time. So here we have a predicted and the data. So the machine learning model learn the relation between these two variables and predict one when we don't have the another. That's it. Thank you very much for this time, and it's a pleasure for me to talk about my research with Grace and have you, Bridget, here. You are a star of Grace area for me, and thank you very much, everyone, for this opportunity. And that's it.
So thank you so much, Bruno, for your presentation. Very interesting. Now I will call a break, coffee break, so we can fix some bugs to have the online meeting with your student. Okay, so let's have this break.
So we have a coffee break now?
Yeah.
Okay, but the coffee is still not there, so
Actually, the coffee's there, but we are waiting for the snacks. Jimagi went to get the snacks. In 5 minutes, he'll be there.
okay, I think we can discuss a little bit.
Yeah. We have like 5 minutes to discuss.
So if somebody has any question or comment, if you don't ask, probably Professor Scanlon will ask you, so it can be more difficult to care.
I have one question for Professor Murilo and group. How are you planning to start working with the flash droughts, like with the historical data sets, or are you planning to use future projections and simulations?
What do you plan to do?
Wait.
The both. The plan are the both with data sets, historical data sets, and then the projections,
Yeah.
projections.
Oh, very
Yes.
nice. Because working with flash droughts in the like historical data scenario is very it's much easier because you have the RF5, you have a lot of different soil moisture data sets. But for the future, it's very difficult to predict soil moisture. And this is what I found when I started working with flash droughts. But now I think one way to work with flash droughts in Brazil for the future scenarios and try to predict something is to work with or hydrological modeling or even artificial intelligence. Because nowadays those programs and these machine learning frameworks, they can predict soil moisture very easily. I think Professor Paulo from University of Mato Grosso do Sul is now working with machine learning, but for streamflow. But we are already started to work with the machine learning for the soil moisture. So maybe you can connect with him and start to thinking about.
Yes. Thank you, Ballarin, and you are welcome to participate to this project. Priscilla talked with Professor Noemi from University of Rice. She also mentioned some soil moisture products to use, but Priscilla will focus majorly and firstly in this concept of flash droughts. There are global scale flash drought studies have been published recently, but they all use the same concepts of flash droughts. For example, some percent decline of soil moisture, and we like to think is there only one concept for flash droughts? Maybe there are different concepts of flash droughts, different metrics in the Brazilian biomes, something like this.
Maybe they are not working for us here with our context.
Priscilla, are there many examples in the past of flash droughts in Brazil? People talk. I mean, the only time I've ever really heard about flash droughts in the U.S. is in 2012 in the Midwest. They call that a flash drought. And so, will you also be looking at recovery from flash drought, or does a rapid onset, last a long time, or does it recover fast also?
The global studies mentioned the events, the flash draw in Brazil, but the form generical, you know. So we will study, focus on the biomes, on the regions of the Brazil, for for understand if it's occurring actually in Brazil, and if which biomes, for example, you know.
I have a general comment. There were many presentations, very young students doing very nice jobs. Most of them were working in a very general scale, not only specific focus on São Paulo state. And this is a very positive aspect. Another very positive aspect is that inside this room we have 3 universities, very strong capabilities, plus a federal agency, which 4 agency, because there was this guy Schwambach from Embrapa. So this is also a very positive signal of how we can benefit from each other and work together. So all of the pieces, the rain variability was very important. So when I'm coming from the south, so my family was very heavily affected in this flood that you have seen in the television. Many people from my family, they lost their houses and everything. And I'm a very good friend of Walter Corichon, who is a very talented hydrologist here in Brazil, and we were speaking, his family, there were many losses in his family also. So we were very affected and very worried, and within our conversation, it came the idea that how important is the rain measurement and how less rain measurement we have in Brazil. So this is something that I would like to raise to the audience so that you can do your own thoughts about it. And recently we were studying the north of Minas Gerais state, and there was a very long time series for the rain. So 40 years, which is very good. When we took the 40-year series, we realized that from 93, starting from 93 up to now, the trend of the rain was completely different. It means we were there to look into the water availability for the river basin. If we had we taken the whole series, we would come to a different number in terms of water availability if we had taken when it started another trend. I don't know if you got the idea. So this is exactly a break. Exactly. So this is kind of new. I mean, it was new for us because we had in our mind this idea of taking the longest series as possible. So, but the trends they changed. So this is another issue that I would like to raise. I mean, just we can comment about it.
It's me again. I'm sorry that I have a lot of questions, but I'm a curious guy. And my question is to Professor Didier. And Professor Didier, I was joking with him that he uses a lot of tools. He's almost an engineering guy right now. And I do really appreciate your work. And it was really nice to see some work in Ceará, that's my hometown, home state. And more nice to hear from a professor from São Paulo say that we manage war better than São Paulo. And indeed, we have a long history with water because there are no a lot of rainfall in that. But anyway, my question is, before 2012, to drill a well in Ceará was really difficult. I mean, to ask the permission because you need to asked the Environment Agency, I've asked the COGER, and I asked a lot of bodies in the government. And in 2012 was a big drought. They stayed for 6 years, and after that, the government changed the law to drill a well. So right now, it's quite easy to drill a well. You just need to fill a form in the internet, and the government changed the law because even the government was difficult to prove that when they are drilling well that they are not causing environmental impacts. So there are any publications or any studies that show the impact of this policy in Ceará? Do you have any idea?
No, but maybe in the files of COGER that are mostly available at the internet, maybe we can do some kind of research. But I think that this liberality in drilling permissions take parts all over Brazil. In São Paulo state, we are living that. So we miss a lot of information because now it's easy to get a permission to drill a well. You don't have to make available the information or the logging of the well. There is no so for us that we are working and dealing with groundwater is a miss of information, and this is a shame. And I guess also this is a kind of direction done by the government. So we need a kind of economic development. Doesn't matter the environmental cost. If we need water, okay, groundwater is a good option. Make easy to drill wells, not make easy to share water or to think about how share water. This is my point of view, even in Ceará or in São Paulo.
Yeah, I think we can. We can move to the coffee break, and I don't know, in 30 minutes we will be back with a lot of new presentations. We have the presentation of Carol. She's a doctoral student from with Professor Didier, and now I think she's in the University of Washington, right? And I think she's working with the Guarani outcrop zone, and that's it. Yeah, yeah. Okay, so the floor is yours.
Thank you. I will share my screen. No. Do you guys see it?
Yes, yes.
Okay.
You can start.
Hello. Okay, so I will start. Hello, everyone. My name is Carolina. I am a third-year PhD student at the São Paulo State University. I work with Professor Didier, but currently I am on an exchange internship at the Washington State University in Pullman, and I'm working with Professor Jamil. So before diving into my presentation, I would like to extend a heartfelt thanks to Jessalyn and everybody in the organization of this event on making it on a hybrid format, allowing me to join you today. So today I'm going to present on a significant project we concluded last year, titled Hydrogeological Studies to Evaluate the Exploitation Conditions of the Guarani, Bauru, and Serra Geral aquifers in the Water Resource Management Unit 12, the Baixo Pardo Grande. So the logos on the bottle are the institutions involving in this project, which we'll get deeper further. And the logos at the top right are from the scholarships I've been fortunate to receive. So this was a 2-year project, and our study area, as I said, was the Baixo Pardo Grande watershed that is located on the northeastern region of the São Paulo state. And for this project, we brought together a multidisciplinary group that include community and members of the university community, such as the LAHIA and the LHC labs, led by Professor Didier and Professor Edson. We also collaborated with some water resource management agencies, such as the Department of Water and Electricity of São Paulo State, the Baixo Pardo Grande Watershed Committee, and the Autonomous Water and Sewage Service of Bebedouro City, one of the largest cities in the study area. So funding from this project was provided by the São Paulo State Water Resource Fund, and financial manager was made by FUNEP. So, with a project at this scale, many hands contributed to its success. And before introduce everybody, I would like to take a moment to acknowledge and thank you everybody's work, because much of this project results forms the foundation of my PhD thesis. So, for this presentation, I'm summarizing our products in 3 main tasks. And for reference, GW in my presentation, it stands for groundwater. So first, we starting consolidating a groundwater GIS database with valuable help from Lia, Amanda, Bruno, and Pedro. Next, we gathering all groundwater samples that we could find in literature, also conduct some groundwater sampling campaigns, and analyze it for hydrochemical and isotope content. This stage of the project was conducted at the Environmental Study Center that is home to LAHIA, with the assistance from Marcela, Ariane, and Bruno. Finally, we made the modeling of the Guarani aquifer groundwater and prediction of scenarios based on water use, and this part was led by Elio, a former PhD student of the LHC, and Professor Edson. Ultimately, we use all this data to suggest priority action zones to manage and prevent environmental impacts on groundwater in the basin. So the study area is on the northeast portion of the state of São Paulo, close to the border of Minas Gerais. The study area here, may I get, oops, pointer? Okay, so this is our study area. The main stream flow is the Pardo River that flows from the estuary of Mogi Guaçu and the Grande River. The basin is home to over 4 100,000 people, and the land is predominantly used for agriculture, mostly sugarcane. And this sugarcane fools the sugar and ethanol plants in the basin. So the basin enjoys substantially rainfall with a mean rainfall of 1,500 millimeters per year. This is the hydrogeological conceptual model that we developed during the project. And as you see on this figure, we have on the west side of the basin, the confined Bauru aquifer. It's a sandstone aquifer. On the east, we have the Serra Geral semi-confined volcanic aquifer, which gets deeper and is confined by the Bauru aquifer on the west. And beneath all of them, we have the Guarani aquifer system. That is a confined sandstone aquifer in the basin. I understand that the LIT students works mostly with its outcrop zone, but here in this basin, he is totally confined. And the Bauru aquifer is recharged by rainfall, while the Serra Geral aquifer is recharged both by rainfall and mixing with underlying water from the Guarani. And the Guarani aquifer in this region presents fossil groundwater that is older than 22,000 years, so it's not recharged at all. So going to our products, the groundwater GIS database was created based on open access and governmental data source. That means we look into the groundwater information systems from the Geological Brazilian Service and the DIA. We look also into scientific papers, water rights permits, remote sense hydroclimated data, and land use and land cover data. In all these databases, we saw information on the wells in the water right status. We also look into stratigraphic profiles, the aquifer, pumping tests, groundwater level and measurement dates, and hydrochemical and isotopic groundwater samples. So this table, I'm presenting all the data points that we could find, but after filtering and refining, we only retain about 20% of the regional information. These are some GIS products example. Here on the left, we have the land use and land cover maps that you can see the shift from the pasture lands used to agriculture, as I say, specific, mostly is sugarcane. Here on the middle, we have on the top the mean rainfall distribution maps, and on the bottom we have the mean potential recharge maps. And as we can see here, the western portion has a higher potential recharge. That is because the Bauru sandstone aquifer. And here on the right, we have the wells density map, and we see that the largest cities of Barretos and Bebedouro, they rely heavily on groundwater uses. Going to our groundwater samples, in addition to the one that we found in the literature, we collected 50 more samples for hydrochemistry and isotopic determination, some of which we also determine the age. So the whole database samples present hydrochemistry data, and more or less half of it present isotopic data, that means oxygen 18 and deuterium, and a few of them representing age data based on tritium, radiocarbon, and heliocrypton tracers. So here we have the Piper diagrams for the aquifers. As we see, they share some similar groundwater type, mostly calcium bicarbonate groundwater types, those circles in green. And secondly, sodium bicarbonated water types, these circles in blue. So with the isotope data, we created the oxygen 18 isoscapes that are here on the left. And based on that and the distribution on this plot, we created a multi-isotope conceptual model. This is one of my thesis results so far. So the first group that we see here is formed mostly by groundwater from the Guarani aquifer that present a depleted signature and are older groundwater. The second group here that is plotted close to or above the local meteorological line water from Rio Claro that represent enriched samples that they may be directly recharged by rainfall. And this subgroup A are the samples from group 1 and 2 that share similar oxygen 18 signatures. So we think that they may be some groundwater mixing samples. The third group are the samples that are below the local meteorological water line and has enriched signatures, and because of where they are plotted, that may mean that the evaporation process occurs during recharge. And the fourth group here on the right corner, there are enriched younger groundwater that we are still looking if it also can be some kind of mixture. Okay, so going into the Guarani Aquifer groundwater modeling, we use the analytical element method. That is one of the specialties of Professor Edson's lab. And for that, we use all gas groundwater historical data that we could find and divide it between time periods. So here on the right, we have the hydraulical head before the exploitation of the Guarani. And here on the right, we have the two first time periods. And despite the limited data point, we see that the model is well calibrated because they present mean absolute errors of 13 and 10 meters. So here is the model for the most recent period. And here on top, we have the hydraulical head. On the middle, we have the groundwater depletion based on the 19 scenarios, that is the scenario before exploitation. And here on the bottom, we have the depth of the groundwater level. This depth information is critical because when the aquifer gets deeper, the variable costs will increase, such as energy from pumping. And just for compare, we are monitoring Guarani Aquifer well in the city of Bebedouro, and the model shows us a depletion rate since the 90s of 3 meters per year, while in our monitoring well, we saw a depletion rate of almost 2 meters per year. So we predicted several cases of scenarios, but we think it. What if the urban surface water use shifted to groundwater? And what would happen if the agriculture is expected to increase, as we saw from the land use and land cover maps? So Elio, he simulated that for us, and as we see here, when the exploitation is expected to increase, we also see increasing in the total mean depletion and the depletion rate. So in the worst case scenario, that is in this column, we see that is when all the urban surface water use shifts entirely to groundwater, and we have an increase in groundwater use for agriculture purpose of 20%. We see a total mean depletion of 105 meters that will occur within 61 years. But when we look again at our Bebedouro monitoring well depletion rate, our depletion rate is already higher than this worst case scenario, which means that we may reach it sooner than we expected. So what if we pursue some more effective use of the Guarani aquifer waters, aiming for reduction of its usage? We also simulated that, and we find out that if we have a 25% reduction in current pumping rates, we would expect a recovery of 30 meters in groundwater depth within 35 years in the Barrentos municipality. So the key takeaway here is that the patient, if the Guarani aquifer was a patient, is sick, but not yet in the intensive care unit. What I mean is while the Guarani aquifer is under stress, it is not in a critical stage, which means we have time to act and prevent it from reaching a crisis point. So with that in mind, we saw that in this basin, there is currently no need to define areas to restrict and control the administration and use of groundwater as expected from some deliberation of the Water Resource Council of the São Paulo State. However, we do need to make proactive measures to make a stopgap from this worst case scenario. So for that, we propose some criteria separated for the unconfined and semi-confined to the confined aquifers. so that we would expand would represent their hydrogeological difference and characteristics. So for that, we use as criteria the kernel, the wells density maps, the registration of contaminated areas, the IO concentrations indicators of anthropogenic contamination, and specifically for the gas, in addition to the one that I mentioned, we also look into the historical groundwater depletion, the results of the monitoring, and the results of the projected scenarios from the modeling. So these are the zones that we are proposing. We identify 4 priority levels based on the severity of the overexploitation signs. That could be definitive, strong, moderate, and tenuous. By doing so, we identified that the critical municipalities are the cities of Bebedouro, Colina, Barretos, and Guaíra. So we see that the basin is impacted by environmental challenges, including groundwater depletion, changing climate patterns and rainfall variability, the anthropogenic contamination, the land use and land cover change, and the geogenic contamination. And for addressing those, we propose 12 actions. While I will not go into details in all of that, I would like to highlight the 4 key actions that can create a foundation for us to implement in the other ones. So the first one is creating a real-time situations room for water resource, and this could act as a daily data source for supporting management in making informed decisions. A second action would be invest in programs for monitoring the groundwater level of aquifers. Currently in the basin, we only have 2 monitoring wells that are from the BAS, and we have another 2 from the gas that are maintained by us in La Ria. And 30 and 4, I summarize then into motivating the groundwater users to share their well information, both on construction data, such as stratigraphic description, and also to water use data, such as the volumes they are using and the groundwater level and other kind of information. So to conclude, this project was a good example of how integrating multidisciplinary data and multidisciplinary people can yield results that support water resource management. Another thing is that our proposed actions align with existing water resource management policies, so we don't need to worry right now about creating policies, but rather focus on implementing these actions. Another thing is that the analytical elements methods is an excellent tool to address the Guarani groundwater behavior on confined parts. It allows us to make predictions that are powerful resource for managers. It also has a huge potential for replication on other basins where the Guarani aquifer is confined. And to summarize, for better management, we need more, better, and continuous data. That means investing in monitoring systems, creating water resource situation room, and training staff to deal with these tasks effectively. As for future research, on my PhD next steps, we are just finalizing a manuscript about the recent impacts that we observe in the basin and how it's related to the water cycle complexity. And moving forward, I will address this future water cycle complexity based on the climate change database created by one of the students of Professor Edson, the Clean Brazil database. That is a great database, I super recommended it. And other thing, in addition to that, what I'm working on is the application of AI classification methods on the groundwater samples. Right now, I'm trying 6 different methods or so. And I believe that will help me to define the hydrogeological characterization of the basin and also better address the groundwater mixing in this complex context. So thanks again for having me, and thank you for the stimulation presentations we have had, and I will be more than happy to answer any questions you might have. Thank you.
Thank you so much.
Sorry if I spoke too fast.
No worries. It was a very good presentation. Now I will open for questions. So does anyone has any questions for Carol? I have one question. So,
Go ahead.
how do you intend to use the climate change projections in your to model the water complexity, water cycle complexity?
So what I'm thinking is that I have a lot of time series of the past of the behavior of the water cycle, and then I tend to use this database to take out the future time series and then combine them, see if they match, and use a long short-term memory method to see how one, like in this database, we have precipitation, temperature, and so I want to correlate that and see how will this affect the other water cycle functions, such as the evapotranspiration, the runoff, because I have the data from the past to train
Okay.
this model. So this is my main idea for now.
Okay. So
I'm just
no,
starting
no.
to try it.
Yeah, I think it's a very good approach. So use some other variables that we can assess in the future to try to, how can I say, explain the water complexity with those variables. And if the machine learning know how to do this, then we can use for the future, right?
Yes, exactly.
Okay.
That
Very
is.
nice, very nice. So
Thank you.
I think we don't have more questions. No. Yeah, yeah, we have questions. Professor,
Oh,
I think you
thank you.
need
That's
to
nice.
close. So Professor Bridget Scanlon will ask for you. She's here now.
Hi, Professor. Nice to meet you.
Nice to meet you. Very good presentation. Really enjoyed it. So I was a little confused. It seemed like you were showing total depletion of 90 meters. And then you mentioned, I think, that you saw 2 meters per year in the wells. So
Yeah.
was that 90 meters over what time period?
The 90s from the time that we modeling the last period. So 90s from 2020. But our monitoring well, the historical data, it just starts from 2008. So it's a short period. So that's why we may have this difference.
So you had 90 meters depletion from 1990 to 2020 from the model.
Yeah.
And was this for the municipality, for Barretos?
It was it's the mean from the whole basin.
And from pumping the Guarani?
Yes, from pumping the Guarani aquifer.
Right. And so you are looking at future climate change impacts on the Guarani, but is the recharge to is the Guarani mostly confined or unconfined?
It's totally confined. So these climate changes in the future that I want to address is mostly for the water cycle on the surface. We're not looking into groundwater because of that. In Guarani, we will not have recharge.
Okay.
So these scenarios is based only on the increasing of the pumping.
Okay. Thank you very much. Great job.
Thank you.
Thank you, Carol. I think that's it. We don't have more questions. So now I would like to invite Jessila. Yeah, Jessila or Diman? No. So I will invite. Okay. So I invite Samuel to talk a little bit about his research, and then after him, Jessila will talk and Dimagi. Thank you so much, Samuel.
If I leave the room.
Yeah, I think you can close because you are attending by the watching the YouTube, right? Yeah. So you can close the meeting now, and we will keep on YouTube, okay? Thank you so much, Carol. Yeah.
So, good afternoon, everyone. My name is Samuel. I'm a PhD student at University of São Paulo. My advisor is a Professor Jamil Anache, and today I will present our research focus, which is analysis of the water cycle and greenhouse gases emissions in Brazilian Cerrado. Our team is composed of by Professor Jamil, myself, and Luisa, Heitor, and Beatriz. All of them are master students. So, its project, the global population, will reach 9.7 billion by 2050. And with this, the production of food will need to increase 1.4 and 2.2 times for provide food for everyone. And the scenario, Brazil emerges as a potential global food contributor. An expected 40% increase in its current production up to 2050. But we know climate changes poses a threat to the agricultural production because can shifts in precipitation, temperature, and evapotranspiration. And this can affect the future hydrological process and water availability. But we have a question. What causes this climate change? We know existing manufacturers, but we can cite increase in greenhouse gases emissions. According to 2023 IPCC report, if the global public policies remain unchanged, we will have an increase of CO2 emissions, as illustrated by the red line in the graphic. And with the increase of CO2 emissions and the other gases, these increase can lead to some problems, such as global warming, climate change, rise sea levels, and others. And again, we have a question. What causes this gases increase? And again, existing manufacturers, and we can cite changes land use and land cover. As an example, we have a Brazilian Cerrado with 2 million square kilometers and covers approximately 23% of the Brazilian territory. And an important curiosity, the area, this area, it's equivalent to be combined areas of Germany, France, England, Italy, and Spain. It's a big area. Moreover, the Brazilian Cerrado is responsible for 55% to the total meat production and for 50% to productive agricultural, particularly for key crops like sugarcane, soybean, wheat, and corn. Unfortunately, agricultural expansions result in the loss of nearly 50% of native forest vegetation, and this causing a land use and land cover change, increasing of greenhouse gases emissions, generating a climate change, affecting the agricultural production, and finally having a potential impact of global food security. With this, our team think 3 research questions. The first, what is the impact of land use changes in the water and carbon cycles? Second, how do plants interact with water and carbon and respond to environmental changes and land use? And finally, it is possible to occupy land in a way that does not impair the water cycle and reduces greenhouse gases emissions. To respond these questions, we chose as our study area Onça Creek watershed because it's located in the Brazilian Cerrado. It's outcrop area of Guarani aquifer system, and it's occupied by different agricultural cover types like eucalyptus, citrus, sugarcane, pasture, and this is an example of land use and land cover change. To analyze the water cycle and greenhouse fluxes in our experimental watershed, we will use empirical models like Pinamonte equation to obtain the evapotranspiration, and to obtain net ecosystem and exchange equation of Runkel. But to obtain these data, we need to do some field data collection. And we will be employed for this purpose eddy covariance and flux chamber, one flux chamber. What is eddy covariance? Eddy covariance, it's equipment for collecting meteorological data like wind speed, gas concentrations, air temperature, atmospheric pressure, and solar radiation. Along with eddy covariance, we will use a flux chamber to obtain the water flux and carbon flux, and a soil monitor. And an important detail here, the configuration of the chamber depends on the type of vegetation. The chamber to be used in the research will have dimensions of 1 cubic meters. Okay, we can see these in the 3 pictures right here. But why using these 2 techniques to obtain the same data, flux water and flux CO2? Because the eddy covariance, it's responsible to data acquisitions of above the canopy. And the flux chamber, it's responsible to obtain these data under the canopy. And with this, we have a better data acquisition. Finally, with the field data collection and apply empirical models, we will do an calibration between empirical models and hydrological model, as an example, SWOT. And with this, we can simulate the future scenarios. As an example, future scenario only eucalyptus. A second scenario with eucalyptus plus pasture. And a future scenario 3 with eucalyptus, pasture, and sugarcane. Our work was divided as illustrated in the board. Luisa will study wetlands and using a flux chamber and eddy covariance. Heitor. Sorry. Luisa will study unsaturated area. Thanks. Heitor will study a wetland and using a flux chamber and eddy covariance. And I will study both areas and using both techniques. And plus to this, I will do some simulate with SWOT. And with this, we have some expected results. One is visualize the impact of land use changes What I mean is using a hydrological model to simulate and visualize a water cycle and greenhouse flux, and with this, make some future scenarios. And creation of a scientific database. So it's create a database and assist scientists, specialists, and decision makers. And with this, have an efficient and strategic use of water and contributor to inventories of greenhouse gases emissions and sequestrations. I appreciate your attention, and I want to thank you, EESC, LHC, USP, and CAPS, and everyone. Thank you.
Thank you so much, Samuel, for your presentation. Very nice, very important for us. And does anyone has any questions for Samuel? I think you can go. You are free now. And I will invite now Dimagi to present a little bit his work for us. The floor is yours.
Hey guys, good afternoon again. So now I'm gonna, so I had the pleasure to be here to be talking in the beginning of the afternoon. Now I'm gonna summarize some of the findings that I had during my PhD. Let me see if it's working. Was the slides working for which one did work? Okay. Okay, this one's great, thanks. So this is the title for my PhD thesis, which I just had presented 2-3 months ago. So it is a double, so it had to use the past finally. So it was a double degree agreement between University of São Paulo and Lund University in Sweden. So my thesis title was called Hydrological and Erosional Dynamics. So I was studying the response in changes in land use and climate in the Cerrado biome. And since we have just a short time, I'm going to summarize some of the topics, just a few parts of the main whole thesis. So we're going to have like just a couple of slides, just 5 to 10 minutes. So the specific goals that we're going to be looking at today are two. The first one, we're going to be looking at the changes in land coverage. So I mean here, the land coverage Cerrado, soybean, pasture, sugarcane, compared to extreme scenarios, which are the bare soil. So we're going to be looking at the trends for the last 10 years and what we had learned during the monitoring on those experiment plots. And then further, we're going to be looking at the interactions between soil, vegetation, atmosphere, and how those factors were interfering in soil loss and water balance during the climate change scenarios. So summarize the first topic, we had to be looking at what are the conditions that we were monitoring those water balance components and erosion. So we had 6 types of plots that were covered in different land covers. The first one, it is sugarcane, soybean, pasture. So those were the agriculture scenarios, and then we were comparing them to the native forest, which is the wooden cerrado, but then comparing to a most extreme scenario where it is the bare soil. And since those plots were created 10 years ago, a couple of years ago, 2-3 years ago, we saw that during erosion for so many years, we saw that the surface had changed completely over the years. And so the erosion process was so intense that pretty much the first layer in the soil were devastated. And so we had to install new plots to understand if the long-term process in erosion were actually affecting in a way that it was not representative anymore. So those were the experiment plots, and it was located around 40, half an hour, minutes driving from here. So it's kind of close, and so those were the sites, site 1 and site 2. And the monitoring occurred for 10 years between November in 2011 and May in 2022. We had monitored more than 200 field campaigns with almost 3,000 erosive events. So it's quite impressive database. Was able to be heading the field monitoring for the last 6 years, but then Jamil, which was also a professor here, was the one that was taking care of the field in the middle, and then some other colleagues were taking care of that in the monitoring in the beginning. So it's quite impressive monitoring that our group was taking care of. So moving forward. So now moving to the first topic, where we're going to be looking at how the interactions in the different land covers. Oh, sorry. So there. And so another point that I have to be looking at when we look at the data is that we are talking about a very, very sandy soil, as you see here, with more than 80% in sand. And during to erosive events, you see that on those pictures there, that the water that is drained out of the experiment plots were pretty much covered in soil, which explain why that area is completely susceptible to erosion. Oh, sorry. So that's the first topic. And here's a summary of the results that we had for the last 10 years. In the drops, we see the runoff in terms of millimeter per year. And then on this pie of soil, we see the amount of soil that is lost in terms of tons per hectare per year. You see, of course, that as we were expected, that better soil had a much higher susceptibility to erosion compared to agriculture. But, and of course, when compared to agriculture to the natural forest, which is the wood and cerrado, we had much higher erosion, also runoff in agriculture. And when we compare the agriculture plots between themselves, we see, for example, that pasture had the higher runoff in terms of millimeters per year, but then when we look at into soil loss, we see that was not actually in pasture, but it was found actually in sugarcane. So it gives us a glimpse that there is something actually going on, that somehow some agricultural land cover are producing more runoff, but then it's not leading to actually to a higher soil loss. So we'll try to understand what is actually going on. And then we created this figure where we are able then to compare one land cover to another. And so inside of that plot, we see here that we can be using that figure to convert from one certain land cover to another land cover. And so we're going to be looking at into one specific example. Imagine that we're going to be switching from sugarcane to pasture. What is the expected change in terms of in terms of runoff or in soil loss? So in that specific case, we found that if you're going to be switch one area from sugarcane to pasture, it is probable that you're going to be find 3.4 times higher runoff, but then you're going to be finding a 3.6 times less soil loss. So that it is a very applied example that how we can be using the field monitoring to expect or to estimate the soil loss or the runoff in other areas. On this figure, we try to understand what is actually going on in terms of why some of the land covers are actually leading to a higher soil loss than in terms of runoff. On this figure, we have the accumulated likelihood of occurrence of soil loss. You see that most of the figures that most of the land covers that somehow has any type of vegetation are very together, and they are very steppy and very far away from the bare soil plots. And when we compare those to the likelihood occurrence in terms of runoff, those curves are very, very apart from each other. And so we can affirm that somehow land cover has a high influence in terms of runoff than in terms of soil loss. And when we compare that figure before, where we saw that one land cover conversion from one certain type of land cover to another leads to a high, like 3 times, 4 times increase in terms of soil loss or in runoff. So we have to see from here that somehow land cover is really affecting the hydrological events. And somehow perhaps, even though I did not study in my thesis, it's affecting, of course, the infiltration that is recharging the aquifer. Now moving forward in terms of climate change and how that's linked to soil, vegetation, and atmosphere, and how is that connected to water balance and soil loss. Of course, I already know, so just summarize, when we talk about climate change, we have to understand that those models, they are just splitting the globe into grids, and inside of each grid, they are presenting all of the atmospheric phenomena, hydrology, and so on. And so that's how the climate models works, but I already know that. So in my thesis, I had been using 2 specific conditions. So I was using the SSP 245 and the most extreme scenario, which is the SISP 585. And I also had the pleasure to be using the data set that we had created, led by my friend and colleague. So we were using CLIMBA, which is the climate change data set for Brazil, which is just focused on those 2 specific scenarios as well. And when we looked into the specific site that I had presented before, which are those experiment plots under different land cover, we saw, for example, from a specific rainfall, we are expecting to have an increase in terms of the mild scenario, but also the most extreme scenario, and not only for the intermediate future, but also in the far distant future. And that can be varying from 5 to almost 10% in terms of median data. And those increases are also expected not only in terms of rainfall, but are also expected to occur in other variables, such as, for example, the maximum temperature and wind speed. And so we have rising conditions, and those conditions that are somehow impacting for sure in the erosion, but also in the water balance components, as I'm going to be presenting in the following slides. So when we're talking about soil loss, we have to remember ourselves of how soil loss occur and what are the main drivers in soil loss. The first one, of course, it is the rainfall, the intensity and the duration of the rainfall, but also some other variables such as pedology, land cover types. But in this case, I was including in the specifications of the model that everything is going to be looking as it is presented now, and the only thing that's going to be changed in the future, it is the rainfall. And so I was focusing studying how the changes in the future rainfall, how that's going to be impacting in the occurring soil loss. And so we're looking now on this part, and to show that the model was quite accurate statistically with the monitored rainfall. And so between 80 and 2010, the climate change models, the mean climate change models were quite accurate with the local observation, and we were able statistically to use those models to predict how soil loss is going to be looking like in the future. And this is how it looks like. And so in the mild scenario, we are predicting a 4.5% increase in the soil loss due to the increase in the rainfall temperature, in the rainfall yearly intensity and duration. And when we look into the most extreme scenario, which is the SISP 585, we're expecting a more intense change in rainfall intensity that's going to be leading to a higher soil loss of around 7.6% by the end of the century. And now moving forward, how climate change is going to be affecting and impacting the water balance. We looked into just 6 variables. The first one is soil water storage, bottom flux, infiltration, surface water flux, evapotranspiration, and finally root water uptake. And in the mild scenario by 2070, we are predicting an increase in root water uptake of about 15%. And there is a hierarchy in those factors. And when we looked into how that's going to be by the end of the century, we're expecting an increase that's going to be stronger. And when we looked at into how is that going to be on the most extreme scenario in climate change, those changes are going to be even more intense, following up the same sequence of parameters that we saw before. And so what is that actually meaning for us? For example, if we're going to be looking at just one variable, which is the root water uptake, it means that for sugarcane, we are expecting a higher root water uptake. So it means that we're going to be need in the future to have irrigation to support that crop. And so it means somehow that we're going to be changing the water availability to support agriculture for that. And specifically for us in the state of São Paulo, which is mainly supporting sugarcane, it means that somehow we're going to have to adapt the entire ecosystem to support that culture in the future. And also is linked somehow to how we're going to find energy in the future if you're going to also keep the same grid that is based on alcohol. So the key findings that I had today, the first one is that land cover has a high influence on runoff than on soil loss, as I presented on the first couple of slides. We also saw that due to climate change is expected an increase in soil loss between 4.5% and 7.6%, depending on the climate scenario that we're going to be using. And that climate change is affecting certain water flux more than others. And so the hierarchical sequence from top to bottom is root uptake, evaporation, surface flux, infiltration, bottom flux, and lastly, soil water storage. And lastly, and it's completely on the same side that Bridget talked before, that land cover changes are threatening soil loss at higher level than climate change. So somehow it's linked to what Bridget mentioned before, that not only climate change is going to be affecting the water availability, but also, and on this case, mainly the change in land cover. Thank you very much for the time and attention today.
Thank you so much, Dimagi, for your presentation. Does anyone has any questions for you, for Dimagi? Yeah, let's go.
Thank you, Dimagi, for your great presentation. It's a doubt. Do you feed the hydros model with climate change data, precipitation? Yeah, and why do you have a box plot? Why do you have several data set in that graph?
Mm-hmm.
Thank you.
Yeah, thank you very much, Murilo, for your question. So on that figure, let me get back here so everyone can have the same question and know what we're talking about. So the variability in that box plot, it's due to the different climate change model. So we had several models, and instead of making just a mean of the data, the raw data, we created like, by the end I had like 200, 300 different models that I had to feed one by one with the different climate model. And so by the end, I was just analyzing how each model is going to be looking like separately. So like we had that discussion before, that makes more sense. Instead of making the mean of each climate model, it is better to just create it, the whole scenario isolated, separated, and then by the end look at what are the results going to be looking like in general. So it makes more sense instead of just making the mean of temperature, the mean of solar radiation. So there were like 6 variables that you had to include in the model. And so by the end, you look at the different models that you have, and then you analyze how each model is going to be looking different at different time frames and also different climate change scenarios. So that's why. Thank you. Completely. That was like a huge discussion that I had during my PhD defense, because the model that I was working, which is Hydrus, it is Vadel zone model. So it's completely focused on vertical. It is just 1D. It is completely 1D. So it's focused just, and on this case, it was just like using a few meters on the Vadel zone. I was not completing up to 10 meters. It was just like 5 meters, depending on the root system depth of each crop. So unfortunately, Hydrus, it is, as I mentioned, a hydrological model that's focused on vertical flow up to a certain couple of meters. And even though it has growth, development that's focused on vegetation, it does not talk well when we're talking about climate change, because I know that considering the climate change, it's going to be affecting the concentration of CO2, that's going to be affecting the plant development, and that's going to, and for example, under certain days of very long heat, plants might not support, and so it does not include that. So the only variables that was considering during that model was the changes in temperature, which means like maximum, minimum temperature, solar radiation, wind speed, rainfall, and a couple of other variables. So I was changing those variables, but I was not changing other variables that somehow is affecting the plant development. And unfortunately, hydro is not well coupled with agriculture in a way that you can for sure ensure that it is completely in strength. So it is something that we need to develop more, or perhaps create a new model, or perhaps talk to some of the guys that are working with hydros in a way that you can completely couple climate change to make sure that it makes sense. Thank you. Thank you for the question.
Very, very nice presentation. Your presentation was also very good, and they connect with each other in a very nice way.
Yeah, we talked before, so that's why like.
So it's just 2 comments. Yesterday in the morning in the breakfast in the city where we are doing the field work, there was in the television a program, the Globo Rural.
I love.
Yes, it's my favorite program. And they were showing irrigation schemes in sugarcane around this area. So it's already it's a reality that they are getting. I mean, the sugarcane needs irrigation to keep the production in a higher rate, and it has lots of things to do with your the last variable that you just show us, and the last GRACE figures for the whole country, according to my colleague Klibik at the Geological Survey, points out that the Cerrado is the biome that has lost water, storage water, mostly in the whole country compared to the other regions. So it's really a hot spot. So I think research like this one, or your issue, looking for what's going to happen in the Cerrado are more than welcome, because it's a very vulnerable biome that we should keep more or less intact.
I completely agree. But one thing that I'm going to be looking at the future is how to expand that prediction to the entire biome or to the entire country, because it is the trade-off in terms of if you're gonna, that is completely based on local preservation. So like I had to feed the model with local preservation of soil moisture and water components that I observed and monitored for 10 years. But how is that, how can I create a model that's accurate for the entire country? And how, and how to predict that, how that's gonna be looking for the entire biome in 100 years from now. So that was like another point that I know it is a limitation, but all the time you have to deal with either spatial resolution or with broader spatial resolution. So it's either temporal or spatial resolution that you have somehow to give up. On this term, I had like to give up spatial resolution to have a model that's somehow accurate. And so like I had to reduce as much the uncertainties, but at least it was based on field monitoring.
Do you have any idea if other research groups are doing something different in central or north portion of Cerrado? Because Cerrado cross at least 3 or 4 climatic zones in Brazil, and so it should be interesting to figure out and to make some comparisons between what you are observing here in Minas or Bahia or whatever.
Yeah, I know one group that was doing something similar in Paraná, and they did for the entire state, but they were not able to have field monitoring, so it was completely based on, for example, satellites. But I'm not going to take some of the more time. We can keep talking more in the future. We are running out of time. Thank you very much, you guys, and I'm
Thank
sorry.
you, Jumagi. Now we have the presentation of Jessilan. He'll talk a little bit about his work. So the floor is yours.
Zone? I'm sorry. Of course, you can have some impacts on rivers, for example. And the idea of this project was quite simple. Can you get some insights for water resource management using data from the ground for river-aquifer interactions? So the main methodology was based on one of the works of Professor Scott Iacinco from University of California, Santa Barbara. And as our idea is for management purpose, we are doing a quite simple methodology. We are taking the well water elevations and the elevation from the streams. So they are quite easily to get in the field. And as well, we are using first principle of physics. The water comes from high elevations to low elevations. So if the well water level is above the nearby stream, it is a gaining river. And conversely, if the well water elevation is below the nearby stream, it is a losing river. And of course, for that, I have to take data from the wells. So I take the data from the Geological Survey of Brazil. There's this data, CIAGAS. CIAGAS is a great database. Unfortunately, there are no harmonized database. So we have to do a little bit of working, but a lot of people of Geological Survey of Brazil help us. So now we have, from the total database, we have about 115,000 wells. They could be used in your study. And just for your information, we are working with Geological Survey of Brazil to publish this database so it can be accessible to everybody. But here, my purpose was just to look for the well water elevation. If you look to this figure, what is interesting is that there was a lot of yellow and green. They show that the well water elevation in Brazil is quite shallow. Indeed, more than 50% of the well water elevation is above 10 meters, so it's quite shallow in Brazil. And of course, I have data from the wells, and many of you are asking right now that maybe the wells and the rivers, I mean the aquifers and the rivers are not connected, because they need to be connected to have these kind of interactions. So the hypothesis, we made 3 hypotheses to kind of get wells and aquifers. There are aquifers and the rivers, they have some interactions. So the first hypothesis is the well could not be more than 1 kilometer from the nearby river. The well's depth could not be exceeded 100 meters. And of course, the wells could not be it must be in free aquifer. Here I show you a cross-section of Gainer River, follow our methodology. And so we have addressed the database from the wells, we have addressed the interaction, and of course, right now we need to address the data from the rivers. And it would be lovely to have data from the rivers, like, I mean, the elevation of the rivers across the Brazil. The USGS has this data. In Brazil, unfortunately, we don't have. So I have to think a little bit more how we can do that. And was the big problem for us, but what we did, we take the digital elevation model, I mean the elevation from the digital elevation model in the river, but when we do that, we take likely the valley floor or the food plan, not exactly the level in the water in the river. So to do that, we have to estimate this variable that we call bank full high. And to estimate this variable, we have to develop some equations for each biome in Brazil, or for each basin. So we take almost 500 Brazilian stream flow illustrations that we have this data. So we can put in an equation and estimate the bank full high according to the drainage area from the river. So with this equation, we completely our database. I mean, we have data from the wells, we have data from the river, we have kind of first order interactions between the rivers and the aquifers. So you can go to the results. And here are the results. As you see in figure A, we have a lot of red saying that most of the wells have water below the near river. Indeed, most of the wells has water levels below the near stream river. And many of you can think, why is this important? This is really important because before this work, everybody thinking that in Brazil we have a lot of gainer rivers, as we did in the US before the work of Professor Scott Yacinko. And our work is showing not exactly they are losing rivers, but potential losing rivers, because I can tell you only the directions. I can't tell you the real flux, because for that I need a lot of data that is impossible at the national scale. And so we look to the regions of Brazil. There has more than 60% of the nearby wells below the stream surface. And what you can see is most of them are in Brazilian drylands. They are as expected, but as well in some basins that are really important for us, like the São Francisco, and as well in some regions of the state of São Paulo, they use a lot of groundwater. And in the map B, I show you the drylands, as well the areas in Brazil in green. The more than 20% of the land are under cultivation. And so we take two important basins as a case of study, and there are the basins in B. There are São Francisco, and the C is the Verde Grande, and there are a lot of papers about them, and we take them because they are quite important for Brazil, as a lot of guys are talking right now. The Verde Grande is a critical basin, as reported by ANA, the national agency, because the demand is quite similar to the supply, and they have a lot of issues there. In the São Francisco, we start to have some issues in this basin. So we show that we have in these basins, most of these basins have potentially losing rivers, and that could be a problem because we are expecting a lot of increase. Indeed, we are expecting more than 50% increase in the coming 20 years, following the last report by ANA. And of course, for us was kind of surprised this result. And of course, we made a lot of sensitivity analysis to show the results are robust. And indeed, we compare our analysis with local studies as well. And just to try to understand if these potential losing rivers are losing water or not in the following years, we take data from 40 stream flow rivers. There are following or is to the potential losing rivers, and we apply the simple methodology just to see if there is a trend in the stream flow and base flow. And indeed, for the potential losing rivers that has more than 30 years of data, they show negative long-term trend in base flow and stream flow. Of course, I cannot tell you this negative long-term trend is related to pumping, but is a first result, and of course a lot of other works need to be done to confirm that. And I need to conclude, of course, this oil study is a pioneer effort in Brazil to looking for river-aquifer interactions here, and of course we need a lot of other studies to show to support our study. But indeed, we show that the prevalence of losing rivers in Brazil, or at least potential losing rivers, and they are concentrated in drylands and cultivated areas. And we show some relation between the decline of groundwater levels that can affect surface water. And of course, I have to acknowledge a lot of other guys that have done amazing jobs to show the interactions between river and aquifers, like Thais in the 40s, Winter in the 19s, Lenny in 2020, something like that. And of course, we hope this work can help, can have some impacts on the policymaker here in Brazil, as we can see water as a one, I mean, the interconnection between surface and groundwater. And as I said in the beginning, I have to acknowledge a lot of guys that helped me Some of them are here, like Ballarin and Professor Didier. And of course, I have to acknowledge all the support from the Geological Survey of Brazil. Thank you for your attention, and I hope I can answer some questions.
Thank you so much, Jessila, for your work. I cannot talk too much because I am one of the co-authors, but congratulations for your hard work. I believe this study will pave the way for different groundwater studies in Brazil. Does anyone has any questions? Okay, we have one co-author with questions. Yeah. Okay. So.
Really nice presentation, and congratulations again. Did you have a buffer zone? So your groundwater depths are pretty shallow, and did you have a threshold level where you said you don't know whether it's gaining or losing because it's within a certain level and there's uncertainty on all of those things?
Actually, there was this question is one of the questions that the review one from my paper asking, and so we plot as well the difference between the rivers and aquifers, like here in Figure 6, for different regions of Brazil, and we show that they are quite different. I mean, there are some river aquifer that they have difference from 2 meters or 3 meters, but most of them is 5 meters of difference.
Right. Yeah, and you said in the 40 stream gauges that you looked at, about half of them were also losing. I wonder if you ever see long positive trends in discharge, because it would just discharge. I mean, it wouldn't keep increasing. I don't know. It would just flow away. I mean, would you expect to see, do people see increasing trends? You said you saw very little increasing trends, but would you expect to see increasing trends because it would just discharge?
Yeah, actually, Professor, here we take 40 streams from the Anache, but we take as well some other databases. And in this database, we can as well work with data from climate. And we have shown that there's a lot of bases that are increasing, a lot of bases that are decreasing. But we don't, from the bases that are decreasing, we don't have strong trends in the climate, at least from precipitation and evapotranspiration. So here from these losing rivers, I can tell you, to be honest, I can tell you only that they don't have a lot of difference between the climate. I mean, don't have trends in the climate, but they could have trends, for example, in land use, and that the land use can impact as well the stream flow here. So, and of course, other things that we done in our work was to correlate the difference, as you asked, between the rivers and aquifers, and the amount of pumping that we have in Brazil, and they are correlated. But the problem is we don't have a really confident data from the pumping in Brazil. But there are some correlations.
Right.
Statistical correlations.
And we were out in the field on Sunday, and you were surprised that it was losing, And so you do this large scale, and then you're in the field and you're doing really detailed scale,
yeah, exactly, yeah.
And so it must be hard to go back and forth.
Yeah, it's hard. It's hard, and I put in the title here, long-term river-aquifer interactions, because I mean almost every river is gaining and losing water. What I'm seeing here or show here is most of the time is a losing river, most of the time is a gaining river. I can give you an example. In the Congress, in my section was a guy from Pernambuco. They showed the data from the Beberibe River. And the Beberibe River is most of the time a losing river, but in the raining months, like 3 months in the year, it is a gaining river. our work show there's a losing river. So it's quite expected, as expected. But like I said, the river can be a gaining river, but most of the time is a losing river. I answer your question?
So just one last question.
Okay.
No, not a question, just a comment.
Yeah.
So I interviewed somebody from New Zealand, the Southern Island, and they were doing a lot of work with isotopes and everything on base flow, and they were really surprised because the water's running off the mountains, the Alps in New Zealand to the plain, and they expected that a lot of it was just surface flow, but they were coming up with estimates of 90% base flow.
Base flow,
Yeah. So, a lot of, but they didn't anticipate.
Yeah, sorry, Professor. It was really difficult to do this step here to compare with local studies. I mean, we have, at least to my knowledge and to knowledge of the Web of Science and the Google Research, about 30 studies of local river interactions here in Brazil. It's for the Brazilian size is nothing. Most of them are done by Professor Didier or by Professor Edson. And so we could not compare our data with local studies. But as I said in the beginning, this methodology was introduced by Professor Scott Yasenko. In the US, they could compare with local data. And they show that for most of the data, yeah, the methodology is good. I mean, is similar to the local studies. But we have a lot of problems with local studies as well, because we have a bias. Like, we have a lot of studies that show they're gaining, but we don't have a lot of that show they're losing. I don't know why. I don't know why. Maybe Professor DJ can help me answer that. But at least here in Brazil, before this work, everybody thinks that we have a lot of gaining rivers. The losing rivers are just in the dry lands. Yeah. And for example, one of the PhD students of Professor Edson have shown that the Jacaré-Pepita, that some of the guys know here, is a big river here, has some section there's a losing river. And yeah, so there's this kind of thing there. There are some losing rivers even in São Paulo. And because that's not depend exclusively or only for the climate. Of course, the geologic, the soil, the land use and whatever can change that. Yeah. Go ahead, Professor.
So, 2 questions to think about. How many of these rivers can become not perennial rivers? So we think on gaining rivers all of my life, I think on that, and now we are looking at some of those rivers are losing rivers. It's something that could be explored in the future, how long it will take to the southern part of Brazil become a semi-arid region is one point.
I can answer this question.
Yeah, but I have a second comment. It's not a question. Okay. It's only a comment. And the second one is a question. Do you think that some of this behavior on rivers can be related to the overpumping of confined aquifers that can, by the decrease in water levels, create a leakage from the unconfined aquifers and remove water from the system down instead of going to the rivers? So this is a question. The first one is only a comment.
No, but the first one is actually, I want to do something related to the first one, because one of my co-authors is Professor Yang Fan, and Yang Fan has a global model. Indeed, a lot of people have global model, like Yang Fan, Petra Toll, the Ingraf. And the good thing about the model of Professor Yang Fan, it is a physical model. They don't need calibration. And he has applied for a lot of applications. They show good agreement. And I will try to see if it has a good agreement as well here in Brazil. And his data, we can see actually the groundwater level daily. So with the groundwater level daily, we can try to see some ephemeral rivers, like if the groundwater level is always below the bottom of the river, is an ephemeral river. And this has been done in the US. I forgot the name of the authors, but he has published in Science. So it's a great paper, and he has using the model from Professor Yang Fan. So I'm trying to mimic that for Brazil. So it's one thing.
Like a projection for the future, and okay, we are in the
yeah, exactly.
turning point.
Yeah. Yeah. So, but one limitation is the groundwater pumping, because we don't know, we don't have good data about that, and the model of Professor Yang Fan don't consider groundwater pumping. So that's one of the limitations.
Is responsible by that.
Yeah.
I think pumping.
Yeah.
Pumping is more important than climate change.
I mean, a lot of your work also suggested land use changes.
Yeah, sure. Sure.
So
it's kind of
Sure. Let's just me finish my talk.
Assume, emphasize the amount of water pumped from the aquifers based on the land use.
Yeah, indeed. Just sorry, it's just to finish my thought. Indeed, Mark Birk, I'm not Birk. Yeah, has as well as a model, and the model has an economic model. They're based in the variables economic in the region. They put some demand in the groundwater, is some demand in the surface water. Maybe I can use that, but as well, it's just a model.
I remember when I did the comparison of models and rates, that PCR global water balance showed the opposite effect on the Amazon or whatever than many of the other models. I mean, these models are,
Yeah, like Jamil said, we should use a lot of models and maybe see if there are agreement or not. Do you have something to talk?
No, I have just a comment.
Yeah, sure.
I don't know if everyone online can hear me, so because I don't know if the guys online can hear. It's just to complement how difficult it is to assess climate change in context of, and on top of that with change in land cover, because well, how can we actually predict how the change in climate, the change in land cover? Like, we don't know how, if you're going to be expanding the deforestation in the Amazon, if you're going to be able to reduce to zero. So it's completely unpredicted from one year to another. So like a couple of years ago, we had a very lower deforestation, and then it really increased. And then we are reducing again, and so it's completely difficult to predict how we are going to be using land in the future. So that's why like most of the papers are not dealing with that yet. I hope perhaps in the future we're going to be able to couple somehow and actually ensure that we are talking about changes in the land cover in the future, but for the moment we are only able to assess the changes from one land cover to another in a hypothetical way.
Sure. And there's I need to answer the second part of the question of Professor Didier. Okay.
Yeah, we have another question.
They ask about mining groundwater. Was that?
Yeah, no, not mining groundwater, but I was interested on that. So we are pumping capture water from confined aquifer, and you change the flow nets.
Sure.
And you can take some water from the upper aquifer and bring down instead of.
This is the topic of your thesis?
My master's.
Your master's.
My master's.
Okay. I think the models, large-scale models, are very nice. I really appreciate it that you have done this with Ciagas. But I think it would be very, very interesting. For example, if you choose different rivers in different geological frameworks, just like you did with San Francisco and Verde Grande. So one from the semi-arid region in your home state, in Ceará, one in a coastal area, which is more flat, where you have those multi-layered aquifers, another one in the very hilly regions, and then you do like a cross-section, really like a conceptual model after, and by combining it, so that, because then you would give to us, to the whole community of hydrogeologists, very well done conceptual models of the river aquifer interactions in different scenarios. So, and talking about the Verde Grande, so keep it as a pilot project for a cross-hatching like this, because the geological survey, we are just finishing a very, very, very large, very well done, conducted hydrogeological assessment. So all the information you need for the Verde Grande is going to be there. So you can really take the Verde Grande as an example and really go very deep in which part of the river it gets disconnected from the aquifer and it's not perennial anymore, and why. So keep it as a pilot project in your next.
Thank you, Roberto. First, of course, I use here for the river the digital elevation model, but all the data is from the ground. So I'm not modeling nothing. I just data from the ground, and the idea was have a first kind of look for Brazil. Yeah. And that's really great, your question. Indeed, we try to do that. We correlate all variable here with a lot of other variables. We try to do that. But unfortunately, like in the large scale researches or large scale studies, the correlations are not strong enough. So it's a goal of us, maybe with modeling, we can do that. Maybe looking at specific regions, we can do that. But right now, unfortunately, cannot. But I must say that, for example, here we have, indeed, what I was very conservative because I use only 3 aquifers, not confident aquifers. But for example, in the US, Professor Scott Yasenko used all the wells, even in confident aquifers, but they must not the deep must not exceed 100 meters. And there was a kind of issue for me because this reduces a lot of the wells, because most of the wells in Brazil are in confident aquifer, like Professor Didier said. But yeah, there's something that I definitely want to do. And if you remember, I asked you to be my master defense, but unfortunately you could not be there. But there was a great question. And to answer Professor Didier, I really don't know, to be honest. But at least we correlate our water level difference between the wells and the nearby stream with thousands of variables. And one of these variables was the amount of area there was in the city, for example, and there was not correlation. I don't know, there could be, but at least our data don't show that.
Yeah, I'm interested because in the work that Carolina has presented, we're looking on the base flow at Pardo River, and we observed a trend of decrease. And one of our hypotheses, it could be, okay, Pardo River basically is fed by basalt, by the Serra Geral aquifer. If we produce a decrease in water level in Guarani aquifer, you can, or you may have some kind of inversion of flow. Instead of have upward flow, we have downward flow, so reduce the amount of water available in the basalt so that it's not too much, and then impact the base flow. So it's something that I'm very, very interested, because nobody thinks or pay attention on this situation.
Yeah. And just to conclude, I want to say that like every large-scale studies, of course we have some limitations, but at least we are discussing that. At least we remember of capture that we unfortunately forgot. Like Professor Bridget said, we take 2 steps ahead and 1 step back. And one thing that maybe my work will help is to show at least some regions in Brazil where we need local studies. Because unfortunately, like I said before, most of the studies of river aquifer interactions are made in São Paulo by only 3 or 2 professors. So maybe we need more studies with combining modeling, combining this work, combining local studies. Maybe I can answer Roberto in the next years, and maybe try to show some conceptual models from losing gaining rivers with different setups, climate setups, and geological setups.
For sure, Gisela, I think top-down approaches are very always welcome, and nobody cares here in Brazil about groundwater because nobody sees groundwater.
Sure.
But when we start to show them that groundwater is changing, this is the first step. And then after this, we will have probably more studies to confirm this. And I don't know, maybe they will show the opposite. Okay, but we are just giving them the first, first click, yeah. So thank you so much.
Thank you guys for your attention and for the great questions. I look forward to discuss with you more. Thank you.
So now I think we are reaching to the end. I'd like to thank, in name of the Professor Edson and Jamil, first of all to Bridget Scanlon to being here, and I hope you had a very good time today. We really appreciate your visit here, and also we need to thank Professor Didier, Roberto, Murilo. Thank you so much for being here and to discuss with us and showing your presentations. Thank you so much. All of you guys.